yeah, this is a problem right here. I wish I would have had the forethought to ask, well, why is it a problem? I didn't think about that. I don't want you to be as ignorant as I. What is the significance of a molecule being made from an alkane into a transalkene? What is the importance of that? It is more stable. That's kind of important. What else? What is this stereochemistry important for? What is stereochemistry? Yes, Ron. Like what enzyme? Fumarase is an excellent answer. Yeah. And is anybody here of Italian descent? What does fumare mean in French? In Russian. Just to irritate you, Zaleski. What's fumare mean in?
It's not Russian, it's Polish.
Either way. All the same. Those Slavic areas, who gives a crap, all right? I guess I do give a crap, because it's not Russian. You're right, I do care about that part. And that means that they probably didn't help Trump out in any way, although you never know. Somebody's going to come forward pretty soon. Bottom line to this, what does fumare mean in Italian, do you know?
No, I think yes, it means fire.
Yeah, it does mean smoke. And the reason you would call it this is because the molecule, when you're oxidizing it, it's just like when you're smoking things, or you're burning them up. You're burning it, and you might have seen this before, maybe at international airports and things like dietato fumare means no smoking. That name comes from this molecule is an oxidation taking place. That is not the important part of this name. This trans molecule is recognized through fumarase. The cis molecule is not called cis fumarate. It's called, listen carefully, maleic acid, or maleate, not malate. All right? And what does the prefix MAL mean? You don't have to be of Italian or Polish descent to know what mal means.
Bad.
It means bad, because maleic acid, the cis form, is a poison of the Krebs cycle. Specifically, it poisons that enzyme, because the cis molecule doesn't fit into the active site the same as the trans molecule does. It does fit in, but it can't react, and it stops that enzyme from doing its job. This is what stereochemistry is all about. Which is why, if you see any molecules, the stereochemistry on Friday is important. When you see molecules like fumarate missing, you have to draw the transform. When you see, the only one whose stereochemistry does not make a difference is that of lactic acid. Because, as I told some people outside of class, in some organisms, the pyruvate molecule, when it's reduced to form lactate, the D form is formed. And in some cases, the L form is formed. And if I'm not telling you that these processes are taking place in you or other organisms, then you don't know which one's going to be. But for everything else, all right, all the other molecules, the stereochemistry is important. And since you're not going to see two structures missing in a row, the stereochemistry from this molecule to this molecule is never going to change, all right? From that to that it changes, specifically to the transform. In this case, I would also let you off the hook for malate, because I forget how important that L form is in this particular situation. But other than that, all the stereochemistry is important to us, okay? I'll let you off the hook for isocitrate, that's not on there too. But you gotta make sure you get the right molecules, okay? Everybody listen carefully, and tell anybody who's not here, if they're your friend, the biggest mistake you can make on Friday is drawing the same molecule in a space such as this one missing right here, but drawing a molecule like oxaloacetate or malate, which is sitting over here in that very place. That doesn't happen any place in glycolysis of the Krebs cycle, that a molecule is made into one thing, then later on that same thing is made. That does not happen, all right? Yet every year, somebody, and usually somebody doesn't know what they're doing very well in these kinds of pictures, will draw a picture of like malate, where it's supposed to be drawn fumarate. Or they'll draw oxaloacetate, where they're supposed to be drawn isocitrate. That should never happen, guys. 2 plus 4, 6, 6, 5, 4, 4, 4, 4, all back to 4, all right? If I draw this molecule here, down here, you get no credit for that picture, all right? And let me think about this. Each picture is worth about 4 points, 4 or 5 points, I can't remember for sure right now, somewhere in that ballpark, all right? And as such, you get 0 if you're drawing the same structure that's someplace else on this process right here. Now those of you who are smart about this say, wait a minute, what if I draw oxaloacetate in another place on process 1, because it's supposed to be drawn there. That's different, all right? Yes, oxaloacetate and pyruvate show up on both process 1 and process 2. And that is a question that's asked about on Friday. I'm not going to say anything more about that. I will say more about it on Friday, okay? Anyhow, this fumate molecule is hydrated, all right? This is hydrolysis here of this double bond to create this molecule, which is L all the time as far as I know, but I could be wrong about that part, all right? The malate molecule is what? What is happening when malate becomes oxaloacetate?
Reduction?
A reduction of what? Maybe you can say yourself. Because obviously the word I was looking for was oxidation, but you say, well, Frost, it's got to be accompanied by a reduction. Yes. Oh, huh?
Redox?
It is a redox reaction, but what is getting reduced?
The alcohol?
The alcohol is reduced to a what? A ketone? That's reduction.
Pass.
Can somebody save Leah from her? Yasmin! You are allowed to raise your hand where somebody else in this room might be able to see it too.
Is it the oxidation of malate?
It is the oxidation of malate, so what's getting reduced?
NAD.
NAD
Plus.
plus is getting reduced to NADH, getting the 2 electrons and 1 proton of hydride. The malate becomes this ketone right here. Everybody else, this is an oxidation of this and a reduction of this, all right? And folks, what's going to happen on Monday is I'm going to say, oh, this reaction, which is, whatever, 22, I don't care what the number is, you can see it on your cheat sheets, all right, is identical to what other reaction? This I do expect a large number of people to get wrong. They're going to say, oh, you're making an alcohol into a ketone, so that's what happens when you make isocitrate. No. When you make, oh, you're going to make alpha ketoglutamate. No, that's not the same reaction that's identical to this, because I don't lose any carbon dioxide in this one. This reaction is not kind of, it is exactly identical to what other reaction? Again, you don't have to even give me the name. All you have to do is be able to recognize it where it is, and it's not on this page right here. It's in process 1. But it's not part of glycolysis. What do you got, Yasmin?
Is it 12?
Is that, which reaction is that? No, you can't, it can't be 12, because you're bringing in a carbon dioxide, right? And you're making that into a 4 carbon, that's not happening right here. There's no carbon dioxide involved. Yes, sir?
Would it be number 11?
It is reaction 11. Guys, look here. If you couldn't see this group right here, couldn't this be malate? Lactate being made into what? If this is lactate, what is it made into? Doesn't that look like pyruvate? Well, we already know oxaloacetate and pyruvate look a lot alike because they are made into each other. Yes, that's a good wrong answer right now. And why would people pick that? Well, it's oxaloacetate, so it's the same kind of reaction. It's not the same kind of reaction. When you make pyruvate into oxaloacetate, you're adding a carbon. You're not oxidizing or reducing anything, right? But you're making oxaloacetate. That is true, but I'm not making the same kind of reaction take place. Folks, why do I bring this up all the time? At some point, if evolution occurs the way that we think that it did, the first organism basically had 1 or 2 catalysts. And then it got more and more complex as mutations took place, and pretty soon it had a bunch of different catalysts, and its offspring had even more catalysts, and some of those catalysts did the exact same thing. The enzyme malate dehydrogenase, the enzyme lactate dehydrogenase, as already pointed out, have the exact same amino acids in the exact same place. They don't have the same tertiary structure now. They're controlled under certain different, they show up in different places. But they're made basically the exact same way because the processes are exactly the same. I've given you 2 other examples, scratch that. 3 other examples of this. When glucose becomes glucose 6-phosphate, fructose 6-phosphate, fructose 1-6-phosphate. Same exact kind of reaction. When the ketones and aldoses are isomerized, glucose, fructose, dihydroxyacetone, glyceraldehyde, same exact reaction, same exact amino acids, very, very similar amino acid and active site structures. When 1-phosphoglucose and 6-phosphoglucose are isomerized, and 3-phosphoglycerate and 2-phosphoglycerate are isomerized. Same exact kind of reaction. Now we've got this and that. Finally, this reaction is identical to what other reaction? It should be on this page, but it's not. It is on your cheat sheets. What reaction is identical to this right here? Yes, Colin?
Would it be number 6?
6 is not on process 2, is it?
Oh, you mean for process 2?
And 6 is not the same because
It's the addition of
6, there's no coenzyme A in any place in glycolysis, correct? Now guys, when I say identical, I mean it's identical, which is
When the acetyl group is formed.
when the acetyl coenzyme A is formed. Again, folks, look here. If my hand is a hydrogen, that's pyruvate. And if pyruvate reacts, it makes acetyl coenzyme A, correct? In this case, I have heard, and you might ask Dr. Boy, or I don't know who else teaches microbiology, if they know which microbe has the same enzyme, not a similar, the exact same enzyme catalyzing both of these reactions, because it does the exact same thing. I pointed out that that enzyme, pyruvate dehydrogenase, needs thiamine, needs apoic acid, needs an FAD molecule. This got exact same things, all right? Again, just slight differences in the overall tertiary structure, but they are basically doing the exact same kinds of reaction, okay? All right, half hour ago I asked Jessica what she wants to know about. I said NAD+, and I've been talking for a half hour about everything, including NAD+. What other questions you want to have answered right now, Jessica? What questions have I asked you you want the answers to? Anybody have any answers? Any questions that they want to have answered? What's wrong there? Huh? I'm not going to give you the answer to all. Pick one. Pick one that's important, that's hard right now.
I don't know if it's important or hard, but which is needed.
Yeah, that's why I was going to ask the
Ah, what does catalytic amounts mean? Can anybody answer this for Leandra?
No, don't call me out like that.
No. Lucine's asking too, and trust me, who else likes this question from Leandra? What does catalytic... Look around for a second. Shh, what do you got, Jackson?
Just things that don't get consumed.
Ah, like catalysts. They don't get used up, but you have to have some present, understood? What are the catalytic things you need for glycolysis? I need the enzyme. Everything else is used up. I don't need glucose in catalytic amounts. I need it in stoichiometric amounts. If glycolysis is going to take place, I'm going to use up a
Isn't
glucose
it
molecule.
FAD?
Or glucose 6-phosphate. I don't use any of the intermediates in catalytic amounts.
But that's in glycolysis.
For the Krebs cycle, that's exactly the opposite. Any one of these guys is needed in catalytic amounts. What do you mean by that, Fust? I have to have at least one oxaloacetate. But I can get that from any one of these guys, correct? So if I give you a citrate, well, then I can make that into oxaloacetate. If I give you a pyruvate, I can make that into oxaloacetate. But then I use it up, but then I regenerate it. So if I pick any one of these guys as the intermediates, the enzymes, of course, are all used in catalytic amounts. You know that enzymes are catalytic, all right? What else is required in catalytic amounts? And you're allowed to say that in this case, Justina. I know I've kind of argued otherwise, but what other molecule is definitely needed in catalytic amounts? Coenzyme A. I use it, I get it back. I use it, I get it back. Understood? That's what catalytic means. Things that are used up, things that are not needed in catalytic amounts for the Krebs cycle. Acetyl coenzyme A. Not the coenzyme A, just the acetyl portion of it. That's got to be attached to that. What else is used up? What else is used in non-catalytic amounts? What's used up the most in the Krebs cycle? NAD plus is the correct answer. For every Krebs cycle, I need 3 of those guys. For every Krebs cycle, I need 1 acetylcoenzyme A. I need 1 FAD, I need 1 GGP. Of those things, which one am I not going to get back in subsequent reactions, and which one don't I want to get back in subsequent reactions? We just heard, I need acetyl coenzyme A, I need NAD+, somebody mentioned the other day, I need GDP and phosphate, that's true, I need FAD. When I have this reaction take place, I use up one FAD and make FADH2, I use up one GDP and inorganic phosphate and GTP, I use up three NAD pluses to make three NADHs, I use up the 2 carbons of acetyl coenzyme A to make what product?
Carbon dioxide.
Carbon dioxide is the correct answer. And of those 5 things that I just said right there, which ones don't I want coming back to the molecules that they were originally, and why not? Only one of them. Guys, guaranteed this question is going to show up someplace on either quiz, the last quiz on Friday, or the final exam, or third exam, maybe the final exam too. What thing don't I want to get back to the original conditions, and I can't get back to the original conditions? The carbon dioxide, because I can't do that. Plants can do that. That's what photosynthesis is all about. I breathe on them, they take my CO2, they can make it back into glucose molecules, not through the reverse of this, through the Calvin cycle and through the like reactions, which we'll come back to in just a moment, right? How do I get the other guys back? Well, we already talked about this. I know how I can get these 2 guys back. This thing reacts with ADP, it becomes ATP, now I've got my GDP back, right? I'll get a phosphate from someplace. How do I get my FAD and my NAD plus back? I got a better question for you that you should already be asking me. Where are all the ATPs I'm supposed to be getting out of this process? As Beth told me before class, you get 30 or 32 ATPs out of the complete oxidation of a glucose. So far, according to the reactions on process 1 and process 2 involved in the complete oxidation of a glucose molecule, one second counter, how many net ATPs have I produced? When a glucose molecule goes entirely through glycolysis and the Krebs cycle, how many net ATPs are produced directly? Jessica, is this a good question?
Sure.
I'm doing online shopping.
No.
Just check.
Are you including ATP?
ATP equivalents, yes. 6 is not the correct answer. Net ATPs. 4 is the correct answer. How am I supposed to get, Catherine?
I mean, well, from glycolysis and the Krebs cycle?
How much? Huh?
4.
That's all I'm supposed to get out of this?
Out of these 2 processes, yes.
Out of the complete oxidation of glucose is what I said.
Oh, out of complete? Well, you take the FADH and your NADH that you make and then the GTP from...
The GTPs are ATP, that's one of the ATPs.
You take those 2 things, the FADH and the NADH from the Krebs cycle and then...
Or from the conversion of pyruvate to acetyl coenzyme A, or from lactate to pyruvate, if you're talking about other reactions taking place, or from fatty acid oxidation, or from oxidation of amino acids, or from the other reactions in glycolysis. All of these guys produce NADHs.
So you take those things
Yes.
and you bring them to the electron transport chain.
Oh. Interesting. What happens in this electron transport chain thing?
Keep talking.
Sure. No one else is rushing in to say noon.
Okay, so there's
I
like
know Beth is, but
a proton gradient is formed in the mitochondria.
it's a big jump right there. You start at NADH and all of a sudden you got a proton
Okay,
gradient.
well, there's like a bunch of shuttling stuff that goes on.
Whoa, 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 there's no shuttling stuff.
I've said too much.
Beth did the exact same thing. I withdraw the question. I take the 5th right there on this one right here. I want to sit down and think about what I'm not going to say anymore. Huh?
That's not how this went.
It's pretty much how it went. Yasmin was right there.
It's not.
Yes, it is. What do you got, Colin?
Alright. Now, the NADHs and the FADH2s are again brought to the electron transport chain with the aid of certain shuttles.
Don't worry about the shuttles yet.
Alright.
I don't need the shuttles in this process. Why not? What shuttles are you talking about? Do you have any idea, Colin?
Now,
Does anybody have any ideas? What things we're talking about shuttling? What do you got?
Is it the FAD and
Nope.
So the FADH.
It is the shuttling of electrons,
Yes.
but not to the electron transport chain from the Krebs cycle. It's to the electron transport chain from what?
From what?
Yes.
NADH.
Where?
To where?
No, from where?
From the citric acid cycle.
No, I don't need a shuttle for that. See, yeah, you got it, smart
Wait,
ass.
from the liver.
No, stop. Take a hint from Katie right there. Just stop right now, just stop. Yeah.
Isn't it going through the membrane of the
From
mitochondria?
where?
The cytoplasm?
From outside the mitochondria. This all happens inside the mitochondria. The electron transport chain happens inside the mitochondria. Fatty acid oxidation takes place inside the mitochondria. So where am I going to get NADHs? I'm not going to get FADH2s. Where am I going to get NADHs produced outside the mitochondria? On which reactions on your cheat sheet am I producing NADHs outside the mitochondria? Do not look at process 2. That happens inside the mitochondria. There are 2 reactions that produce NADHs in the mitochondria.
6.
6
11.
and 11. If I'm starting with lactate, I'm making NAD. But we're not talking about, yes, we can be talking about that. The energy I'm going to get out of this process right here is not in ATPs. It's in the reducing power. That's what I'm going to use to power the electron transport chain because it does need powering. The electrons want to flow from NADH to, where are they going? Where are the electrons that are coming from NADH or FADH2 going to through the electron transport chain? They're going to oxygen, which is why this process really, really depends upon oxygen. And why I don't care about this slide. Look at it for a second. The control of the Krebs cycle. These enzymes are involved. I'm never going to mention them again, all right? I'm not going to tell you anything about the specifics on this slide right here. What I will tell you is that the Krebs cycle is going to be controlled by 2 things. Do I need ATP? Yeah, that's kind of important. Do I have oxygen? Look at your process 2, folks. Is there any oxygen involved any place on that reaction? The answer is no. So why is oxygen involved in controlling this process? Because it controls how much NAD plus I have and how much FAD I have. Unlike glycolysis, well, no, I say like glycolysis. Both of these processes are going to stop when you run out of NAD plus and you run out of FAD for the Krebs cycle, all right? Unlike glycolysis, I don't have any other way of getting those NAD pluses back. How do I get them back just for glycolysis? I reduce my pyruvate molecule to lactate, and then I get rid of that crap lactate. I don't want it. I want the NAD plus. I can't do that for the Krebs cycle. Why not? Because it needs too much NAD plus. It needs too much FAD. The only way I get them back is through the Krebs cycle, and as Kaylee just told me, the Krebs cycle, the electron transport chain, that has to have oxygen to accept the electrons. The electron transport chain doesn't take electrons. It transports them from NADH or FADH2 to oxygen. And when that process takes place, as we will see on Friday, a ton of energy is released. And what do I do with that energy? Not Beth, not Katie. What do I do with this massive amount of energy, 52 kilocalories that is released for each NADH getting oxidized by oxygen? What do I do with it? Some of you are thinking I make ATP. You do not make ATP. Wasim, you know what happens with all that energy. What do I use all the energy that's released for that electron transport chain doing its job to do? What does the electron transport chain do as its job? Maybe you don't know. You look like you're going to answer something. Anybody besides Beth or Katie?
Pump protons.
It pumps protons. Hear the word pump. That takes energy. That disparity in hydrogen ion concentration can be used by a different enzyme that is not part of the Krebs cycle. All right? And what I will be telling you about on Friday is how much energy is associated with this process. You will want to look at the electron transport chain slides and understand this, that NADH is a better reducing agent than FADH2. Thus, it can reduce things better than FADH2 can. Specifically, it can reduce the first part of the electron transport chain. FADH2 can't. FADH2 reduces the second part of the electron transport chain. The first part can reduce the second part. The second part can reduce the third part. And the third part not only can, really wants to, and it wants to give electrons to a guy that really wants them, and that's where oxygen comes in on this whole process. And each one of these steps right here says, so much energy released that I can, as you pointed out, Quentin, and as Beth pointed out, and as Katie pointed out, and other people know this, can be used to pump protons out of the membrane. The question you should all be asking yourself, and I will actually be posting a quiz that asks you this, and I will be giving you the answers. So when you come in on Friday, you say, I know what the answers are, I just gotta find out which is the right answer, all right? Is how many protons do I need to pump out to make an ATP? And the answer is gonna be pretty easy, because we don't have to memorize anything. We're gonna see what the effect of each one of the pumps is in this overall process. Does everybody have a Scantron sheet?
No. I don't have it.
Can you bring them up for me, please? So, very kind. I could have you pass them forward, but you are much faster at getting it done. Everybody in the back has one back there, right?
Send you one?
Yeah, can do.
Wait, I get to interview someone tomorrow.
Again, questions?
Did you get one? No.
I will give you until 12:55 to do this. However, at around 12:56, I have a few things to say about the final exam. If anybody wants to hear about them, not answers to the final exam, of course, but about the way that's going to be administered and talk about this. I also talk about this after class on Friday and on Monday as well. If you want to hear about it, you can stick around and do so, all right? Okay. Questions 91 through 96 are shown right here. Questions 7, 8, 9, and just 7, 8, and 9 are also shown. Answer these questions first.
Do we have our sheets from last time? We don't have our old sheets, we can do.
No, that's what I say. You're doing 91 on this one right here. 91 through 100 on this, and 1 through 10. That's just one sheet. Just do it that way.
Wait,
You heard
1
me
through
say
10,
this.
and
The
then
reason I didn't do that is because last time I handed them out.
I thought you were gonna come up.
No. Just use these.
Oh, this is the first one? Like, so weird.
But 91 through, and face 91. No, it's just that we only have to use one sheet and have to worry about passing anything out. Yes, you may use any sheets that you have. And actually, as long as I don't hear you, you can even talk to each other. But I would not be giving anybody any answers. That's kind of bogus. Ever look at question 1 and at question 7 right now? 91, 7, 2, 8, no, and down. Maybe easier to just do this
Who
one.
knows?
What do you mean by paired? Like next to each other or the same in different molecules?
Give me 1 second. Here are questions 91 through 100, and we'll do the other ones in just a second, okay? Who asked that question? Sorry, what do you mean? We were talking about this the other day, Jackson, right? You know what the right answer, you're supposed to know what the right answers are, right? That means that there's 2 wrong answers in this particular situation right here. One of them could never, ever in a million years be the right way of pairing up the various carbons in a glucose molecule if it's going to be split into 2, 3 carbon molecules, right? In this answer right here, there's only one correct answer. There are 2 answers that could be correct, but they're not. There are 2 answers that are completely bogus, right? Same answer choices right here. There's one that's more bogus than the other one. You know what I'm talking about? Then you pick your favorite letter. Don't pick one of the right answers for which ones are paired. If you don't know it, that's fine. I actually gave this answer the other day, so. Yeah, you guys who are talking, don't waste too much time because we're going to go on to the next questions in just a second, all right?
Wait.
And not a second, but relatively quickly. I'm back. Do that. John Mark.
So some of these have 2 answers?
Well, they might have more than one answer, yeah, put them all down, they're there. I don't remember, I didn't pay attention to whether it's put in a lot like that or not. I guarantee you for the first one, all right, only one right answer. Second one, only one right answer, that's why I say pick one. That's the most bogus.
Ross, does 97 have two answers?
I don't know for sure. Maybe.
So are we using ATP and GTP and chips?
Except for if it says actual ATPs, then they're not the same thing. But if it's an ATP or ATP equivalent, then they mean the same things. Or if it says directly too. Come back. Come back to you, guys. You already have the answers to 9, right? They were on the original quiz, right? So how about 10 too?
So for 8, are you saying net ATP or ATP equivalents or just like produced?
Yes, net. Yes, that's a good point. All right. The key word is directly this, but this is net. All right. Right. There is one correct answer right here. Only one correct answer for question 8. Okay. I believe it's also yes for 6, 7, 5. I think all of these either have one answer, except for these guys right here. I don't know for sure about that. For all these guys that I saw right now, only one answer or 0 answers. That's everything 1 through 8. All right. 9 and 10, I don't remember. I'm not looking at them.
So for number 8, GTP is included